Greetings. Now we will give a lower bound for the best possible randomized algorithm. For the best possible randomized algorithm for the scheduling problem. Now this is just for the practice part, so since I'd like to give you a lower bound for the best possible randomized algorithm, I'll use the Yao principle. That's what it's for. So it's just a Yao principle. How? So when the Yao principle is in action, then we have to give a randomized input in the simplest case. This means that I will guess simplest case, I'm just giving you a sigma 1 input with some probability p1 and a sigma 2 input with some probability p2, which is of course 1 minus p1, such that sigma 1 is a prefix of sigma 2. Prefix of sigma 2. This is again because we will check all the deterministic algorithms. So compute how a deterministic algorithm can behave in expected value give a lower bound for that. This is exactly the same which we've done for the ski rental problem. There were two inputs, so the first one was just b half days, and the sigma 2 was 1/2 b snowy days with a probability of 1/2 and 1/2. And we just compute it by a case analysis. Usually it's case analysis on tau 2 case analysis. On tau 2. Okay, so let's do this. First we have to choose as an exercise. So apply the Yao principle on the following input with 1/2 probability. I give you 2 jobs, each having a cost of 1, and with 1/2 probability I give you 2 jobs, a cost of 1, and a job with a cost of 2. So in this notation, this guy here is the sigma 1 and this guy here is the sigma 2, and you can see that sigma 1 is a prefix of sigma 2. That's why it's suitable for Yao bound. And then we just have to so it's advisable to compute the optimal solutions, and of course M can be say 2. Otherwise, if we have at least 3 machines, then of course the 3 machines can handle each of these. jobs separately, and the optimum as well as the algorithm's outputs would be 3. But if we only have 2 machines, then the optimal solution for sigma 1 is just this guy here, so it's 1. And the optimal solution for this guy is just put the 1 here and put the 1 there and push the 2 here. So the optimal solution is 2 for this case. But you see that here this 1 1 and here that 1 1, which are just the tau 1 and the tau 1 there, while the worst stuff is, so it's the tau 1. These two are very different. So that's the other reason why the choice of this exact sigma 1 and sigma 2 is suitable for Yao principle, because the prefix itself should be arranged in a different way than if we get the wall input. So for the wall input, it should be arranged quite a different way. That's why it will probably give you some bound, which means that so the expected competitive ratio on this particular input ratio is 1/2 divided times the cost of tau 1 divided by 1 plus 1/2 times the cost of tau 2 divided by 2. Okay, so that's basically 4, right? So it's just the cost of tau 1 divided by 2 plus the cost of tau 2 divided by 4. I usually underline the vectors. Okay. This is exactly the same as the one which we checked at the ski rental example, and you can check that video if you wish, just as a recap or reminder. But after we computed how to compute the ratio, there was a case analysis, and again here comes a case analysis as well. So it's a case analysis for what? For the longest, for this guy here. So how can an algorithm schedule this 1 1 2? So the cases are if an algorithm schedules the 1 like this. Okay, that's one case. Another case is if the algorithm schedules this 1 and the other 1 to the same machine and puts the 2 after them. Okay, fine, that's also an option. So, and the third one, which is different from the others, is if the algorithm schedules this 1 here, this 1 to the other machine, and the 2 to, well, again, it doesn't really matter in which order the machines are. So basically we have these 3 cases, and we can just swap the 2 machines if you wish, but that will have the same cost. Now, in this case, the cost of tau 2, which is the longer version, here it's 2, the make span is 2. Here the make span is 4, and here the make span is 3. Now the cost of the tau 1, which I just indicate here, so in that case the tau 1, the output corresponding to the first part of the input, is just given there. So the cost of tau 1 will be 2, and will be 1. And then I'm just substituting these expressions into this larger one. So this will give me, in this case, it's 2 divided by 2 plus 2 divided by 4. In this case, I will have 2 divided by 2 plus 4 divided by 4, right? And here, in that case, I will have 1/2 plus 3 over 4, right? So I'm just substituting. I'm just plugging in the values. So it will be 2, it will be 5 over 4, I've seen this one before. And here I will have a 3 over half, so it's 3 over 2, 1/2, yeah, 1/2. And amongst these, the minimum, again, I have to change the to check the minimum. In this case, I will get that a lower bound corresponding to this randomized input will be 5 over 4. So this means that applying the Yao principle, you can't go with a competitive ratio. There is no, so the end result of the Yao application for this particular randomized input is that there is no randomized algorithm online, of course, for scheduling that's better than 5 over 4 competitive. So this 5 over 4 is a lower bound. Now, the worst situation depends heavily on the actual input, on the actual randomized input. And the folks who just study these type of problems are usually prove lower bounds by defining better and better inputs. Now, how can you improve? Well, we just have to parameterize, for example, the probabilities, like what happens if I'm just giving you the input 1, 1 with a probability of p and give you the other one, the 1, 1, 2 with a probability of 1 minus p. Then, of course, still the optimum for this guy, the optimum is 1, and for that guy, the optimum is 2. That's great. And the expected value of the ratio, so the expected ratio for this particular input is just p times the cost of tau 1 divided by 1 plus 1 minus p times the cost of tau 2 divided by 2. Yeah, 2. That's the option. Okay. Tau 1 and tau 2. Okay. So it's basically p times the cost of tau 1 plus 1 minus p time divided by 2 times the cost of tau 2. Yeah. Now, since we already have this table, and then we just have to plug those values in, and we immediately get that for this part I will have 2 times p. Yeah, so this guy here is 2 times p plus 1 minus p divided by 2 times the cost of tau 2, which is 2 again. Okay, so it's 2, which is just 1 plus p, right? 2p minus p is p, right? Then for the next one, it's 2 times p plus 1 minus p divided by 2 times this guy here, which is 4, Now what's this? So it's just 2, it's just 2, plus 2p minus 2p is just 2, okay? And third, we will have 1 times p plus 1 minus p divided by 2 times 3, which is, I'd say it's 3 over 2, and I have minus 3 over 2 p's plus p, which is just minus p per 2, okay? So using the parametrization with p, we get these, and the competitive ratio of the algorithm will be the minimum. So the competitive ratio of the best possible online deterministic algorithm will be the minimum of 1 plus p, 2, and 3 over 2 minus p half. Okay, and if I want to get a good lower bound, I have to maximize this. So I have to maximize the minimum of 1 plus p2 and 3 over 2 minus p half. We've seen those things already a couple of times, so here I'll just again solve this in a graphical way. So it's 1, so that is the 2, so the 1 plus p part is that guy, 1 plus p. The 2 is that guy, and the 3 half minus p over 2 is just 3 half minus p over 2 is something like this. And of course the minimum of these 3 functions is just this line here. Okay, so it goes downwards. And I want to maximize this. That's achieved at this point, where again, as before, it's 1 plus p equals 3 half minus p over 2, and I'm just adding these p over 2, so that's 3p, and subtracting 1, which is just 1 half, and multiply it by 2/3, I'll get p equals 1/3. In which case, this max of min will be 4 over 3. So, what we have at the end is that with the input, the randomized input, with the random input, so with a 1/3 probability I will give you 1, 1, and with a 2/3 probability I will give you 1, 1, 2. We get a lower bound of 4 over 3, lower bound of 4 over 3 for the competitive ratio of the best possible randomized online algorithm. And that's it. So if you wish, you can try to improve the lower bound for this problem by just choosing some other input sequence with some other probability. So if you wish, you can just try and get better and better possible inputs. Yeah, and Next time we will learn about another version of the scheduling variant where not all the machines are considered equal. But today we just learned a lower bound with an application of the Yao principle for the base version of the problem, which is not a hard example to solve if you know the basic notions. Okay, so till next time, bye bye.